everyone, I'm Dr. Jagadha, Associate Professor in the Department of Mathematics. The topic for discussion we have taken Fourier transforms. Regarding the definitions and terminology we are going to discuss. So the first in detail we will discuss about in this video lecture, definition of Fourier integrals. Next we will discuss about from the Fourier integrals we will obtain Fourier transforms. So that definition we will discuss. Next, the Fourier transforms, which is divided into two types, that is finite Fourier transforms. Next one, the definition of infinite Fourier transforms. The last one, regarding the Fourier transforms, what are the properties are defined to this Fourier transform, that is also we will discuss in detail. So now the definitions we are going to discuss, that is obeying some mathematical laws and parameters. The definitions are defined. To define the definition in a very systematic way, connect to the subject field, what is the terminology we are going to discuss. The first one, the very first formula, the Fourier integral formula, that is f of x, that is a function which is given, which is equal to 1 by pi integral 0 to infinity. So the next one, integral minus infinity to infinity, cos p of t minus x into f of t dt dp. Now, this we are seeing cos p of t minus x. The particular place we are going to replace it by the trigonometric formula cos of a minus b. It's nothing but cos a cos b plus sin a sin b. So now our a is playing the role pt and our b is playing the role px. So in the particular the right hand side of this formula, the capital A we are going to replace it by pt and b we are going to replace it by px. So now we can see it 1 by pi integral 0 to infinity, the next one integral minus infinity to infinity. So the right hand side we can see cos a, that is the particular a, we replaced it by pt and the b we replaced it by px. So this first term we completed. Next we will move to the second one, that is sin capital A. So the capital A we replace it by pt and the capital B which is replaced by px. So the complete the trigonometric, the formula, the substitution which is over. So we can see it. F of t dt dp. How this, from this, we can see it, how the formula we are going to, this is the Fourier integral formula from which we can derive two formulas. Fourier sine integral formula and Fourier cosine integral formula. For that, these are the steps we are going to adopt it. Now, up to here, we are going to write as one term. So the next one, this is, we are going to consider as second. So everything, so this is the first integral completely. This is the one second integral. every term is same. That is this f of t dt dp, we brought it here. Next, this into f of t dt dp. So, what is the question we can expect what we discussed from this slide? State Fourier integral theorem, that formula we can write it this one. So, this is the explanation, the previous slide we obtained after substituting the trigonometric formula. This equation we are naming as 1. Now, our aim is we are going to define from the Fourier integral formula, Fourier sine integral formula. For that, some assumptions. That's what the terminology, which is subjected to our Fourier integral theorem, that we are going to discuss. For that, cos of pt f of t. We can see here, this t is there. The t, we are going to replace it by minus t. Next, wherever t, we substituted minus t. We know very well cos of minus theta, it's nothing but cos theta. So here also, cos of minus pt, it's nothing but cos pt. And we can see it here. So cos pt, this f of minus t, the minus, it has come out. It is f of t. So this is the function we have taken. We replace it t by minus t and we obtained it. So after obtaining just opposite sign, the result we obtained it. The definition of, that is the testing of whether the function is odd or even. So these are the terminology which are subjected to our Fourier integral theorem. And we are going to define Fourier sine integral. For that, the main one, we are checking whether this function is odd or even. Then one more concept, that is, if the function in general, if it is f of x, the x we will replace it by minus x. After replacing, the result, if it is minus of our given function, then we will call it as odd function. But there is no change at all. Even after changing, x is replaced by negative sign. There is no change in the given function. Then it is even function. So, to get the Fourier integral, sine integral formula, again these all we are defining to our main definition, Fourier integral theorem. So now this one we have taken and we obtained it is odd function. Now here we can see it, sine of pt f of t. We will replace t by minus t. Then here noticing pt, it is there. That is t, we are replacing it by minus t. So it has become sine of minus pt. So sine of minus pt, we know sine of minus theta, which is nothing but minus sine theta. So we have written here, this it has the negative sign. Again, f of minus t, it has the negative sign. So minus put together, positive. That's what this is written. Sine of pt into f of t, it's nothing but our same given function. So just now we discussed if after replacing x by minus x, if we again the result what is given, what we have taken the function for testing, if you're getting back the same, then it is even function. Now one thing we are going to do it, that is if it is odd function, especially the integral range from minus infinity to infinity, then the particular integral is vanished. Whereas even function, this in range minus infinity to infinity, the range will be changing from 0 to infinity, that is for even function. So we can see it. The first completely it is vanished because it is an odd function. The second one we can see there is a change in the limit to range. Before it was minus infinity to infinity. Now it is 0 to infinity. So we obtained from the Fourier integral formula, Fourier sine integral, we obtained it. So this is the formula for our Fourier sine integral. That is 2 by pi integral 0 to infinity sine px integral 0 to infinity f of t sine pt dt dp. So what question we can expect? Very short questions. State Fourier sine integral formula. So this can be written. And the more we discussed what is even function, yes, the question. Then we are ready to answer. What is odd function? Odd function, what is the limit it is? Exists minus infinity to infinity. And odd function, then what are the changes will be coming? Totally the integral will be vanished. What is even function condition? If it is even, then the limit minus infinity to infinity will be changed into 0 to infinity. So that we are seeing here. So we can see it here, 0 to infinity. And here also we are seeing 2 into 2 of. That's what the 2 which is kept outside. So this again, we derived it now Fourier sine integral formula. One more Fourier cosine integral formula also from this Fourier integral formula we can derive. For that, we are going to take this only the cos pt we are taking for testing, whether it is odd or even. So the testing, the t which is replaced by minus t. So when we are replacing, that is cos of minus pt. The cos of minus theta, it's nothing but cos theta. We can see it. So it is an odd function. If it is odd function, yes, this integral exists, the limit range will change. And this we assumed, we have taken testing, we have done it. This is even. Suppose in case our f of t is also even, then even into even is an even function. One more concept which is defined, which is connected in a systematic manner towards our main Fourier integral to obtain the result Fourier cosine integral. So the next one is, from here we are taking sine of pt. The testing we are going to do it. So when we are testing, the t which is replaced by minus t. So sine of minus pt, that is sine of minus theta, is nothing but minus sine theta. So our here pt is there. So minus sine of pt. It is an odd function. So we can say it very well. This we tested, it is an odd function. This we are assuming as even function. Odd into even is an odd function. Already, if the limit range is minus infinity to infinity and the function is odd, the integral is vanished. So this one is vanished. The left one is playing the role of Fourier cosine integral. We have to change this 0 to infinity, 2 of the 2 we will put it here. So we can see it, this is the Fourier cosine integral formula. So what is the question we can expect? So for what we have discussed, state Fourier cosine integral formula. So this to be written. So now the definition of Fourier transforms. This Fourier transforms, which is derived from our Fourier integral. Now, straight we will go to the defined formula of Fourier transform. Here, which is written mathematically, capital F of x. The capital F, how we can read this one? That is Fourier transform of function f of x, which is equal to capital F of p. This notation or this notation, both are equal. The formula, which is minus infinity to infinity e power ipx f of x dx. That is, the given function is f of x, which is multiplied by e power ipx, and we have to do the integration with respect to x from minus infinity to infinity. That's what, this is the way the Fourier, the formula which is defined. Now, inverse Fourier transform formula. That is nothing but f of x equal to 1 by 2 pi integral minus infinity to infinity capital F of p e power minus ipx dp. We will do the comparison between this Fourier and inverse Fourier. It is an interesting fact what we noticed here, that is, this f of x, the function is coming outside the Fourier, which is, that is under the integral which is written, that we are noticing, and some variables what is a role playing also. Here e power ipx is there, here e power minus ipx. With respect to x we are doing integration Fourier transform, whereas here with respect to p we are integrating. So what is the question we can expect from this? We can expect define Fourier transforms. Otherwise, the same in a different way of questions. How to represent Fourier transform of the function a capital F of p, otherwise capital F of x. Next, how to represent inverse Fourier transform of function f of x. Define inverse Fourier transforms. So, in a different way, the questions we are asked, then we are able to write it from this what we are discussed. So the next one is Fourier transform formula we discussed. Now Fourier sine transform formula. We can see the mathematical notation here, capital F S of f of x. Capital F represents Fourier transform, and here we can see the notation S. It represents sine, that is Fourier sine transform of the function f of x. Now here, capital F S of p is nothing but integral 0 to infinity f of x sine px dx. We can see here inverse Fourier sine transform formula is f of x, which is equal to 2 by pi. Inverse, if it is there, the Fourier will be under the integration. We are concentrating now Fourier sine. So the Fourier sine, which is under integration, which is multiplied by sine px dp. Inverse, always we will do the integration with respect to p. This point to be noted. So now the Fourier cosine transform formula. Here mathematical the notation is capital F C of f of x. That is capital C of p, which is equal to integral 0 to infinity our f of x, which is multiplied by cos px dx. The next one is inverse Fourier cosine transform. The same, what we have done it, the Fourier sine, the same only Fourier cosine. The difference is wherever s is there, it is replaced by c. Wherever sine px is there, that is replaced by cos px. Remaining and all, just we have written as it is. So if we do like this, where the difference is in variables, Fourier sine, which variable is playing the role? In Fourier cosine, which variable, what is the position it is taking? That to be noted very carefully. So what are the questions we can expect from this? Define Fourier sine transform. So we are ready to write. This is the result. Fourier cosine transform. We will write. This is the result. Next, Fourier transform. It has two types, infinite and finite. So for what we have discussed, it is infinite because everywhere, if it is Fourier transform, minus infinity to infinity played a role. If it is Fourier sine 0 to infinity, Fourier cosine, it is 0 to infinity. But we didn't mention at all it is infinite. The integral range itself, it speaks to us 0 to infinity is nothing but infinite. So far what are the formulas we have discussed is infinite. Now, definition of finite. So now, the finite Fourier sine transform, which is capital F S of f of x, is nothing but capital S of n, which is equal to 0 to L, length of that particular interval, which is finite. That is the reason this Fourier transform, which we are calling as finite Fourier transforms. So now our function is f of x, which is multiplied by sine of n pi x by L dx. Here we can see it. Inverse finite Fourier sine transform formula is f of x equal to 2 by L summation from n equal to 1 to infinity. Here immediately when we are telling the formula itself, it is finite, then why infinity is playing a role? Yeah, genuine doubt is ringing in our mind. Yes, Fourier transform, the finite Fourier transform which is defined, this is L x lies between 0 to L, not for n. That we have to remember. So, capital F S of n, sine of n pi x by L. So, the next one is finite Fourier cosine transform formula is capital FC of f of x, which is equal to capital FC of n, which is equal to integral 0 to L f of x cos of n pi x by L dx. Here we can see it very well. The inverse we are going to concentrate for the finite Fourier cosine transform. The formula which is 1 by L, this we will read it as capital F, that is Fourier cosine transform at the point 0, plus 2 by L summation from n equal to 1 to infinity, the Fourier cosine is which is written inside cos of n pi x by L. So far we have discussed completely Fourier transforms, finite, infinite, all the formulas in detail we discussed. Next, to solve the problems, we will face it. Now, Fourier transform of, if it is given only one function, we are very comfortable. But if there are two functions, then Fourier of first function plus Fourier of second function, that mathematically, how the terminology which is connected to our main Fourier transform is nothing but in a systematic way, assumptions we have done it and we obtained a property, linearity property of Fourier transform. So we can see it here. Fourier capital F and capital G are two Fourier transforms. That is the first one which is connected to the function f of x. The second one which is connected to our function g of x. Then capital F of the complete the function. How we will read it? Fourier of a of f of x plus b of g of x. Is the result what we are obtained is a of f of p plus b of g of p. This is the linearity property which is defined to our Fourier transform, where a and b are playing the role of constants. To define this property, what are the assumptions what we have taken? That is, first we have taken Fourier transform formula for our function f of x. Next, Fourier transform formula for our function g of x. The Fourier transform formula which is written mathematical notation. This how to be read? That is, whatever the function which is given, that should be multiplied by e power ipx, and we have to do the integration with respect to from minus infinity to infinity. So now state linearity property of Fourier transform. If the question is asked a single line in this formula, we can write it. So now the Fourier transform formula is, so this is what we are taking up to here one integral formula, and this is the second integral formula. A we have taken it outside. So a into integral minus infinity to infinity e power ipx f of x dx. The second one, when we are defining the b, we have taken out integral minus infinity to infinity e power ipx g of x dx. So now the A which is written as it is, this is nothing but our Fourier transform. So that's what which is written. The B is as it is, this is nothing but our Fourier transform for the function g of x. So to get the property using Fourier transform, the formula which is playing a very important role to define the property, that is our linearity property. So we can see it here. That is, now we can tell Fourier of first function plus second function, which is equal to constant Fourier of first function plus constant Fourier of second function. This can be written like this also. Same. This also we can write it g of, this is our function. Any way we can write it. Now similarly, this formula is for Fourier. Same manner we can do it for, it is applicable to our Fourier sine also, and Fourier cosine also, which is applicable. Now, change of scale property. If capital F of P is our complex Fourier transform of f of x, then our f of x in the place of x, if it is ax, then the result is 1 by a capital F of P only if it is Fourier transform. But the Fourier transform capital F of P, for that the function is f of x. But now our function is f of ax. Then the P which is replaced by P by a. Our a is positive. So we can see it, our Fourier transform formula, the main formula, we have defined sub-formulas. This is the formula for our Fourier transform. So the state from this, what is the question we can expect? State change of scale property of Fourier transform. Then this is the result to be produced. So now this to define the property, what are the terms we connected to our Fourier transform? We can see it very clearly. Now our f of x, we have now f of ax. So wherever f of x, which is replaced by f of ax, thus some assumption we have taken. ax equal to t, and we did both the sides differentiation. So dx equal to dt by, just we brought this a towards the right position. When we are doing the integration, any substitution, if we are adapting the limits to be checked, that is lower limit is minus infinity. Here we are doing the integration with respect to x. When x equal to minus infinity, the t is minus infinity itself. X equal to infinity, t is also infinity. That is in the particular place we are substituting. So for this particular substitution, there is no change in the limit values. So minus infinity to infinity, this e power ip we didn't touch at all, only x, from which we extracted, we obtained it, we got it, that is t by a, and ax is t, f of t into the dx is dt by a. This from here, the 1 by a we have taken outside. So the remaining one, we can see it as it is, which is written. If it is e power ipx, f of x dx, we will write it, f of p we will write. This is in terms of x it is there, ours is in terms of t. But the t place p by a is there. Then we have to write p by a. This 1 by a, it is written as it is. So the next one is shifting. This property, how we obtained from our Fourier transform. For that, what are the connectivities which is given to our Fourier transforms? What is the terminology that to connect our subjective field of Fourier transform to get this shifting property? If capital F of P is the complex Fourier transform of f of x, then complex Fourier transform, if it is the function is f of x, f of p is the Fourier transform. Instead of x, if we have x minus a, then our Fourier transform, which is multiplied by e power minus pa, that we can see it. To get this one, what are the things we are going to give connectivity of our Fourier transform? This is our Fourier transform formula. We know it very well. That is integral minus infinity to infinity e power ipx into f of x dx. The Fourier transform formula. Now our f of x is f of x minus a. We will assume x minus a, which is equal to t. X from which we obtained t plus a. So dx equal to dt. We will check the limits. When we are checking the limits, x equal to minus infinity and x equal to infinity, the t, there is no change at all. That is minus infinity to infinity. So now, this is retains as it is. This x minus a, which is replaced by t, the dx is replaced by dt, e power ip is as it is, whereas this x is replaced by a plus t. This part we have written outside, and the remaining is e power ip t. We can write it according to the exponential law, a power m plus n. If it is there, we can write under product. So using this basic formula that we remembered, we recollected and we used it here. And f of t dt. So now we are noticing this is nothing but our capital F of p into e power ipa. So the next one, modulation. If capital F of p, otherwise we will call capital F of our function f of x, is a complex Fourier transform of f of x. Throughout the Fourier transform, the capital F represents Fourier transforms. Here, suppose our function is f of x. If it is f of x, Fourier is capital F of p. But now our function is f of x cos ax. So the result is 1 by 2 of f of p plus a plus f of p minus a. To get this, what are the assumptions? What are the connectivities? What are the basic formulas which already defined? We have to recall to obtain this formula. That is everything from our main Fourier transform assumptions that we are applying, and we are obtaining a new theorem, that is modulation theorem. So for this, the Fourier transform formula is, yes, which is written, the formula, that is our function, which should be multiplied by e power ipx, integration with respect to x, integrating from minus infinity to infinity. But our f of x in the place to be replaced by f of x cos ax. So what the question we can expect from this particular slide? State modulation property of Fourier transforms. Quickly we can reproduce it. We can write it well. So now, here this is the Fourier transform formula. This is the Fourier transform formula for our given function. So the f of x, which is replaced according to our function. And this cos ax place, the particular relevant formula, we applied it to get the result of that modulation theorem formula, which is defined for modulation theorem. Now, this into this one integral, this into this, the second integral, two terms are there. We separated the integrals. This two common, which has taken out 1 by 2. So we can notice it, this one f of x, this as it is dx here. The two which is outside. The similar manner, the second integral also 1 by 2 is complete into this which is written here. So this is the previous step. Once again we have written here. Then this using the exponential law, a power m into a power n, the basic, the exponential law, a power m plus n. So this and this we added. When we are adding, This when we are adding ix is common, so which we have taken outside. In this ix, the leftover is p. Here ix, the leftover is a. So e power I of p plus a into x, f of x dx, plus, here also we can notice it, ix is common, the leftover is p, here the leftover is minus a, remaining as it is, which are written. So one thing, if it is integral minus infinity to infinity, e power ipx f of x dx, then it's nothing but our Fourier. E power ipx is capital F of p, but in the place of p, we have now p plus a. So our f of p, that is also we can replace it by f of p plus a. Here also f of, here the p place p minus a is there. So f of p minus a. Very simple way with our main Fourier transform formula, and this formula using, that is cos ax, which is replaced by, and we obtained, this is the result. So now, what are the formulas are there? Finite, infinite, and properties, main four properties related to our Fourier transform, how they are defined, we can see. And this is also, we can take it as one identity. That is, if suppose in case our function f of x, which is multiplied by x, and if we are asked to do it, Fourier sign is nothing but the differentiation, the first derivative of our Fourier cosine with a negative sign. If we do, this is one Fourier transform identity. So the next one result also, these are the defined formulas which are used while solving the problems. This is also the Fourier cosine. If they are asked f of x, if it is multiplied by x, instead of going, that is Fourier cosine transform formula, integral 0 to infinity f of x cos px dx. Instead of going in that route, this way also can be done. We can cross check it. Both will be the same answer. That is f Fourier sine, the first derivative with respect to p, we have to do it. Very long method, integral 0 to infinity Fourier cosine, we know it. F of x cos px dx. This is place we can replacing. It's a very long method, but both the results will be same. These are some identities, standard formulas. Why we have to study Fourier transforms? Because the Fourier transform, which will take the signal and express into in terms of the frequencies of the waves. So the signaling processing, the Fourier transform, which plays a role like anything. Now, so many formulas under Fourier transforms, but forever we have to remember those formulas. Then compulsory we have to do comparison study between the formulas. Same variable under finite, what is the role which plays? Under infinite, what is the role it plays? We can take one for the explanation. Here we have taken Fourier sine transform formula. This already we discussed it. That is capital S of f of x, which is equal to capital S of p integral 0 to infinity f of x sine px dx. This is our infinite Fourier transform. It is not mentioned, but it is infinite. It is 0 to infinity, it is there. The second one, same Fourier sine transform, but it is under finite, where the differences are coming. Here, the notations we have to say up to here, there is no change at all. Here, one notation which is used, P. Here, the notation which is used, N. This is the standard textbooks we referred. That is here, P. It is defined for infinite. For the finite, which is defined, N. F of x. F of x. Here, sine px, but here, n pi x by L dx. So where the difference it has come, where I am circling, there the differences are there. Yes. Here main thing, this infinity only, it indicates as this Fourier transform under infinite. L, this L related to our x lies between 0 to L, which gives an indication that it is under finite. This type of study, it is compulsory. So one we have taken infinite, another one we have taken finite for the same sine transform. So the next one more, inverse we will take it. So the inverse, we have taken Fourier cosine. Inverse, then the function will be outside. Fourier will be under integration. Now Fourier cosine is under integration because we have taken inverse Fourier cosine cos px dp. This is under infinite. We can see it, the infinity, which indicates it is infinite. Now, finite, the same Fourier cosine we are taking. Same f of x function is outside, but we have to remember integral, which is playing the role in infinite, summation is playing the role in finite, where the changes are there. Just I'm circling. Yes, change it is there. This is dp, complete integration. This is summation. And this px, n pi x by L. Two terms are there. 1 by L, capital FC, that is Fourier cosine at the point 0. So inverse under infinite, inverse under finite. For Fourier cosine, the same inverse under finite, under infinite. So we did the comparison. We understood what are the changes are there. Yes, small changes are there. This type of study, we never forget Fourier transform formulas which are defined for it. So the next one, this is inverse Fourier sine we have taken 2 by pi integral 0 to infinity. That is inverse. Fourier will be under integration. Inverse we will do with respect to p. This is infinite. We are doing comparison with our finite. So sorry, here it is written Fourier sine we have taken, here which is written Fourier cosine. So like this, the comparison study, if we do, we never forget. Because of Fourier sine, here sine px is dominating. Here Fourier cosine is there, we can see it. The trigonometric term cos is dominating. So each and every formulas, whatever we have, finite, infinite, inverse, properties, each and every among them, we have to do the comparison. Then we will understand more. So what is the difference between Fourier series and Fourier transform? So this type of question also can be asked. Now Fourier transform is a streamline what we discussed it now. Fourier series which is there, that is the Fourier series which is used for periodic function. Whereas our Fourier transform, we can say it, sum of complex exponentials. Fourier transform, which is used in general for non-periodic functions. So the periodic function comes, we will move towards Fourier series. Non-periodic, we will move to Fourier transform. So we will come to a conclusion of this topic, Fourier transforms. First, Fourier integral theorem. The formula how first we obtained it, from which this Fourier sine integral, Fourier cosine integral, taking, defining, testing, even and odd functions, we defined Fourier sine and cosine integral formula from this. Then Fourier transform, finite Fourier transform, infinite Fourier transform, and we did the comparison study. Fourier sine, what is the role? Same variable if it is there. Fourier cosine, what is the role? Between finite and infinite, what are the differences are there? So among so many formulas, completely what are defined in our Fourier transform, the topic, the definitions and terminology regarding Fourier transforms we discussed in detail. The final we discussed the properties which are connected to our Fourier transforms. Thank you very much to you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.